On January 24th, 1848, a man named James Marshall discovered gold at Sutter's Mill in California. This discovery sparked a massive gold rush in which up to 300,000 people traveled to and settled there looking for gold. Most of the early methods for extracting gold from gravel and sand made use of gold's high density and its tendency to sink to the bottom of pans and sluices as water rushed over the mixtures. Global ocean currents depend on changes in density that result from changes in temperature and salinity of the water. Water that is more dense sinks, while water that is less dense rises. And we see evidence of sinking and rising all the time. Hot air balloons rising, ice floating, rocks sinking, and so on. In 1986, Lake Nyos in northwestern Cameroon suddenly released hundreds of thousands of tons of carbon dioxide into the atmosphere. Because carbon dioxide is more dense than air, the cloud of carbon dioxide stayed close to the ground, suffocating and killing 1,746 people and countless other living creatures. This loss of life would not have happened if carbon dioxide was less dense than air, which leads to a couple of questions. What makes one substance more dense than another? And what factors might play into the observed density of a substance? If I were to fill this box with 40 golf balls and this box with 40 wiffle balls of the same size, which of these two boxes as a whole would have the larger mass? This is not meant to be a trick question, guys. If you've been paying attention in life in general, you probably know that a golf ball has a larger mass than a wiffle ball. So it should make sense that if I put 40 golf balls in this box and 40 wiffle balls in this box, the first box should have a larger total mass. Now let's do it again, but this time we're going to put 8 tennis balls in the first box and 8 baseballs in the second box. Which box, as a whole, would have the larger mass? If you happen to know that a baseball has a larger mass than a tennis ball, it should make sense that the box of baseballs would have a larger total mass, because each of the individual objects has a larger total mass. I know you all are super smart, and some of you are probably wondering, well, what if we compared the box of golf balls to the box of tennis balls? You might know that a tennis ball weighs a little bit more than a golf ball, but there are fewer of those objects in this box. So which box would weigh more? You might have a hunch that the box of golf balls would have a higher mass, and in fact it does. I can feel it. But in some cases like this, you might actually need to get more information, like for example, to put both of these boxes on a scale and see how much they weigh. Now imagine that you have a very small box, say 1 centimeter on a side, and you started stacking atoms and molecules into it, much in the same way as we stacked balls in our boxes. Now you probably know that molecules are really, really tiny, and so even in a box that's 1 centimeter on a side, you could probably fit a lot of molecules or atoms into it. But molecules and atoms all have different sizes and different masses relative to each other, so it makes sense that even our tiny boxes filled with atoms and molecules might have different total masses, much in the same way as our boxes had different total masses with the balls in it. Here I have a bunch of little boxes of varying materials. They're not 1 centimeter on a side, they're more like 2 centimeters on a side, but the idea is the same. We got a number of different substances here: aluminum, 3 different samples of wood, this opaque plastic, a clear plastic, and some brass, some copper, and some, I'm not sure what that is. But even though they have the same volumes, they all have different masses because of the way the atoms and molecules are stacked inside those boxes. I can't see them, but I can measure their mass, and that mass has a special name, which we call its density. To keep things consistent when measuring density, scientists a long time ago decided to fix the volume of the samples that they were going to measure at 1 centimeter cubed, or 1 milliliter. And the density of an element, for example, is defined as how many grams of that element are in that 1 centimeter cubed. So when you look at a periodic table and it says that iron has a density of 7.87 and aluminum has a density of 2.70, that is the number of grams per cubic centimeter of that material. If you paid attention in chemistry class or life in general, you might already know the formula for density, which is density equals mass over volume, or D equals M over V. So if you wanted to find the density of something, you could take your sample, find its mass, find its volume, and then divide them, and you would get a value for its density. We will cover those calculations in a later video. Here we're talking about what factors affect how dense something is. And because we're in chemistry class, we're thinking about factors that involve the atoms and molecules that stack into these little boxes and how they behave relative to each other. To be fair, any mass and any volume unit could be used to measure density. We just picked grams and centimeters cubed because they're convenient. But you might see kilograms per decimeter cubed, or pounds per gallon, or something like that. They're all fine, and some people might use them for specific purposes, but here in chemistry class, we're gonna go with grams per centimeter cubed. The first factor that affects density is the size of the particles that are going into our little imaginary boxes. We can see from a periodic table like this one that atoms come in a range of sizes, from very small atoms like hydrogen or fluorine, all the way up to very large atoms like cesium and barium. And to a good extent, these sizes determine how many of those little atoms can stack into our little boxes. The second factor that determines the density of an object is the mass of the particles that are in it. Some elements have very small masses, while other ones have very large masses, and you can find all those masses on your periodic table. So how can these two factors work together to give an element with a very high density? Well, it might make sense that if you had atoms that were very small in size, and you could stack a whole bunch of them in your imaginary 1 centimeter cube box, and each one of those atoms also had a large mass, you would end up with an element that has a very high density. And the winners of this category are found right here at the bottom of the periodic table, where the atoms have a fairly small size, but also a large mass because they contain a whole bunch of protons and neutrons. So we get values of 19.3 grams per centimeter cubed for things like tungsten and gold, slightly higher values for rhenium and platinum, and the winners are osmium and iridium, coming in at 22.6 grams per centimeter cubed. I know right now a whole bunch of you are out there saying, well, what about the row below osmium and iridium? Shouldn't they have higher densities if this trend continues? Well, I guess so. Those elements probably have higher densities than osmium and iridium. It's just that we don't know them. Those are synthetic elements, and they've only been created in really tiny amounts, and they're not around for very long, so nobody's actually measured their densities. Now let's talk about molecules. It makes sense that if we can stack atoms into a box, we should be able to stack molecules into our 1 centimeter cube boxes. Some molecules are small, and we can easily fit a lot of them in there. Other molecules are much larger, and we have a harder time fitting them into the box. The end result is that each compound, each pure substance, has its own unique density that you can either study or use to identify the substance. A third factor that affects density is molecule complexity. For example, plastics are made of long chain molecules. They might not stack as nicely into our little 1 centimeter sample that we're trying to measure. Plastics tend to have low densities because they're made primarily of carbon and hydrogen, both of which have small masses. However, we could make plastics more dense by swapping out some of the hydrogens with other atoms, like chlorines. Instead of polyethylene, which is just carbon and hydrogen, we might get polyvinyl chloride, or PVC, which is more dense than polyethylene. PVC is more dense than polyethylene because the chlorines have a higher mass than the hydrogens that they swapped in for. So far, we've talked only about solids, but what if the substance is a liquid or a gas? The fourth factor that affects the density is the state of matter that the substance is in. In solids, the molecules or atoms are locked in place and they're really close together, so you end up with typically the highest density in the solid. When you move it into the liquid phase, the molecules start moving around past each other. They take up a little bit more volume, and so only a smaller amount of those atoms or molecules can fit inside the box. And then if you change it into a gas, the molecules are very far apart, flying around independent of themselves, and only a few of them can fit inside our box, so we'd have a very low density. A fifth factor that affects density is the pressure, specifically speaking for gases. If a gas is at lower pressure, there are not as many molecules per unit volume, and so you have a lower density. If a gas is at a higher pressure, then you'd have more molecules smashed into our little tiny boxes, and you would have a higher density. But what happens if the two gases are at the same pressure, but one of the gases has more massive molecules? This is the case when comparing helium to sulfur hexafluoride. Helium can make your voice go higher because it is less dense than air, while sulfur hexafluoride can make your voice go lower because it's more dense than air. Factor number 6 is temperature. Since temperature is a measure of average kinetic energy, higher temperatures mean the molecules are moving faster. When they move faster, they bounce around a little bit more, take up a little bit more volume, and the density tends to decrease. Factor number 7 is intermolecular forces. Some of you may have studied intermolecular forces in a class like AP Chem, and so you know that all molecules have some form of attraction to all the other molecules. This can affect density by limiting how far the molecules can get away from each other or how tightly they're connected to each other. Weak intermolecular forces, like London dispersion forces, allow molecules to get farther apart from each other, leading to lower densities. Stronger intermolecular forces, like hydrogen bonding, often keep the molecules together more tightly, increasing their densities. Apologies here, but don't you hate it when your teacher tells you a rule that's supposed to govern everything, and then later on they tell you, well, there's actually exceptions to this rule? I'm sorry, I have to be that guy right now, but here we're going to talk about water. The general rule is that solids are more dense than liquids, which are more dense than gases. However, water is weird. It's got strong hydrogen bonds between all the molecules, so in the liquid phase you can find them very close to each other, moving past each other, and generally sticking together like little magnets. However, as water approaches its freezing point and the molecules want to get locked in place, they actually lock in place according to those hydrogen bonds and their bent geometries, with bigger spaces between them, making the volume expand, resulting in the density of ice being less than that of water, which is really, really weird. Fun fact, if you were to take a sample of water and cool it down, it would slowly increase its density because it would be becoming more compact. It reaches its highest density at 3.98 Celsius, at which point, if you keep moving down towards zero, which is its freezing point, the molecules begin locking in place and expanding overall, and you get a lower density. And this is huge because ice floats on water because it is less dense. And that means when lakes and rivers and oceans freeze over in the wintertime, all of the life underneath can survive. And why in the wintertime I can go ice fishing, and why an iceberg sank the Titanic, and so on. Finally, we get to factor number 8, and that is the addition of a solute to a liquid to make a solution. In any liquid solution, you would have a liquid solvent, which is what is getting dissolved into. You would have a solute, which is what's going in, and the resulting mixture is a solution. And when you dissolve something in, say, water, the density of the solution will change depending on the mass of the solute particles you're adding. And yes, the intermolecular forces between the solute and the solvent do affect the density somewhat, but this is a general pattern. For example, adding sodium chloride to water adds some heavier ions to the mix, and the density gradually increases to the point where an egg, which will normally sink in water, can actually float in a solution of salt water. In this video, we've looked at 8 factors that affect density: the size of the particles, the mass of the particles, the complexity of the molecules, the state of matter, the pressure, the temperature, intermolecular forces, and the addition of a solute. Every pure substance has its own unique density based on these factors, which dictate how many atoms or molecules can actually fit inside our little boxes. And of course, for many substances, you can look up their densities on, say, the periodic table or Google. But what if you find yourself in chemistry class and you need to determine the density of a substance? Coming up, we'll look at how to find the density of a substance with a lot of accuracy so that you can get an A on your chemistry lab. My hope with this video is that we would all notice the effects of density more often, as they are all around us, but also to think about how density is the result of the interactions of countless little atoms and molecules with each other, and how they might arrange themselves in, say, imaginary little boxes, 1 centimeter on a side. And if we are able to make more sense of the physical world around us, perhaps our knowledge of chemistry might become more solid, or, shall we say, more dense.